Bohr-Sommerfeld rules for the quantization, semi-classical quantization of one-dimensional systems. The rule itself is very simple, although we went through some pain to get it, involving area functions and asymptotic forms and so on. But the basic rule is really simple, and it has a simple interpretation also. It says that the area of the orbit in phase space, which is otherwise loop integral PdX, is an integer plus a half times 2 pi h bar. 2 pi h bar is the same thing as Planck's original constant h. So you can think of the area of Planck cell, so-called Planck cell, as being an area h in phase space. I'll remind you that the origin of this, well, let's see, just to sketch the orbits in phase space for a typical oscillator, there'll be things that look like this. And the quantized orbits are the ones that have an area of n plus a half Planck cells. So the middle one, the center one, has an area of a half. And then after that, it goes 3 halves, 5 halves, and so on. So the area of each little annular region that connects one quantized orbit to the next has an area of one Planck cell. Now, I'll remind you that the origin of this formula is the basic idea that as a particle moves around its orbit, it accumulates a phase, which is the integral of p dx divided by h bar. This is a very old idea and actually precedes even the modern quantum. This goes back to the days of the old quantum theory. In any case, you can imagine it tracing out a wave as it goes around its orbit. Now, in addition to that, it loses a phase of minus pi over 2 every time it passes through a turning point. And since we have 2 turning points in a typical oscillator, that's a total lost phase. And the answer then has to be an integer multiple of 2 pi in order to get phase coherence. I'm just repeating some things I said in the previous lecture. So this has to be equal to 2n pi. And this condition in this form is the same as the condition up above. It's just rewritten in slightly different language. Here, this has to be a loop integral if you're going to go all the way around the orbit. All right. Now, that's the basics of the rule. So I'd like to begin today by making a simple illustration of how we can apply this rule. Let's work with the ordinary harmonic oscillator, where the Hamiltonian is p squared over 2m plus m omega squared over 2x squared, as I guess you know. We'll first think about this classically. If we set h equals e, we get an orbit of energy e. And if we plot this in phase space, x and p, the equation is that of an ellipse in phase space. So it looks something like this. And to use the Bohr-Sommerfeld rule, we're going to need the area of the orbit. Well, the area of an ellipse is pi times the semi-major axis times the semi-minor axis. So let's call this x max here as the maximum position for x. That's the x-intercept of the orbit. We get that by setting momentum p equals to 0, so the kinetic energy term goes away, and then solving for x. And if you do this, you find that you get twice the energy E divided by m omega squared. Likewise, let's call this P max here, which is the maximum value of momentum. That's the momentum intercept. We get that by setting x equal to 0 and then solving for P. So that becomes equal to the square root of 2me, like this. And thus the areas, you can calculate the area without doing any integrals. You can know the formula for the area of the ellipse. It's pi times the semi-major axis, which is the square root of 2me, times the semi-minor axis, which is the square root of 2e divided by m omega squared. Or maybe I've got the semi-major and minor axis reversed, but it won't matter because it's just the product of the two. And you multiply this out, and you can see the masses will cancel. And what you get is 2 pi times the energy E divided by the frequency. Now, by Bohr-Sommerfeld, that has to be equal to n plus a half times 2 pi h bar on the quantized orbits. And you can see we can cancel the 2 pi's here, and then solve for the energy. And the result is that the energy is equal to n plus a half times h bar omega, which you recognize as the exact answer. So without much trouble, for the harmonic oscillator, we get the exact answer. Bohr-Sommerfeld quantization gives the exact energy levels. WKB theory does not give the exact wave functions for the harmonic oscillator, but it does give the exact energy levels. All right. Now, I'm going to run through a series of examples just because it's so easy to do them, and we might as well have some fun just getting some answers. We'll start with some answers we know about the harmonic oscillator. something next to a particle in a box. So here's x. Here's, let's say, x equals L is the size of the box, and the potential energy is that it's 0 inside the box, but it's infinity outside. So these are hard walls. And the size of the box is L. Now, of course, the classical particle just bounces back and forth in the box, like this. To get the orbits in phase space, we need to think about phase space. So let's plot x and p. Here's the line x equals L, again. And the particle is free inside the box. Let's say it has a momentum p0, just to distinguish the momentum of the particle from the variable momentum p here. So the orbit going across on the right side is a straight line with a constant velocity at momentum p0. And when it gets to the opposite wall, it bounces back, which just means it changes the sign of momentum. So it changes to minus p naught and goes back this way with a momentum minus p naught. And thus the orbit in phase space is really kind of a rectangle. Well, it's a discontinuous jump from here to there, because it's a hard wall, but I'll fill it in like this as if it went continuously from one to the other and then back up. And you can see that the orbit is a rectangle in phase space. Now here's the tricky part about the particle in the box. And that is that instead of having a phase shift of pi over 2 at a turning point, we have a phase shift of pi. And the reason is that this is a hard wall. Remember where this pi over 2 came from. It came from taking the potential energy, which would look like this, and we had the actual energy, and then we looked at the wave function in the neighborhood of the turning point. This is what you call a soft wall, where the particle, its velocity decreases in a continuous manner. And there was some complicated analysis to get this pi over 2, although once you get it, it's a simple rule. In the case of a hard wall, the phase shift is minus pi. You can see that because the boundary conditions are that the wave function has to vanish at the wall, and so minus pi means the reflected wave is minus the incident wave. That's needed to make the sum of the two waves be equal to 0 at the wall. So here the Bohr-Sommerfeld condition is going to be that the area, instead of being n plus a half, it's going to be n plus 1 times 2 pi h bar. A slightly modified quantization condition. Now, as far as the area is concerned, however, this is quite easy because it's just the area of a rectangle. The height is twice p0 and the width is L. So this is equal to 2p0 times L. However, p0 is just the momentum of the particle, so that's the square root of 2m. E is the energy. And so I put this in, and I'll get 2 times L times the square root of 2me is equal to n plus 1 now times 2 pi h bar. And so I'll cancel the 2's here. And maybe I'll leave it in the form of p0 for the time being. If I do that, what we get is that p0 is equal to n plus 1 times pi h bar. And then we get the energy E is p0 squared over 2m, which is divided by L. p0 squared over 2m, which is n plus 1 squared, pi squared, h bar squared over 2m L squared, which you recognize as being the correct formula for the energy levels of the particle in the box. Here the n goes 0, 1, 2, 3, so n plus 1 goes 1, 2, 3, 4. The ground state is n equals 1 now, not n equals 0. All right, so that's another simple example. Now, unfortunately, I have to cover this up, but I'll do another example. Yes?
Before you cover that, I'm sorry, I missed the explanation of why we have n plus 1 half when we calculate the quantization for the area for the square well versus, I'm sorry, n plus 1 for the square well versus n plus 1 half.
It's because the one half comes from the n plus 1 half that applied to the harmonic oscillator came from the fact that there's a phase shift of minus pi over 2 when you go through a turning point. It goes through 2 turning points, and that's why you multiply times 2. So it's half of a phase cycle of 2 pi. That's where the 1 half comes from up here.
Okay.
But on a hard wall, you get a phase shift of pi at each wall because the reflected wave and the incident wave have to cancel out.
Oh, okay. So it's
a hard wall gives you a different phase shift, and that's why it doubles the amount of phase, and it becomes n plus 1.
Okay. Thank you.
All right. Now, I'll do another example. This will be the what will this one be? This one will be the rigid rotor. So a rigid rotor, let's do it classically first. A rigid rotor has two masses, M1 and M2. They don't have to be the same. This is actually a model of a diatomic molecule, which we'll come back to in a few weeks. Let's say there's the center of mass right there, so I can put an origin and coordinate system here, x and y, the center of mass. And let's introduce an azimuthal angle. The thing is rotating about its center of mass. Now this is all classical for the time being. The moment of inertia is equal to the reduced mass mu times capital R squared, where R is the length of the rigid rotor, and mu is the reduced mass, so it's 1 over mu is equal to 1 over mu1 plus 1 over mu2, like that. Now, the classical Lagrangian is kinetic minus potential energy, but for a rigid rotor, this is a free rotor. There is no potential energy, so it's just the kinetic energy. And as you know, the kinetic energy of a rotor is 1/2 the moment of inertia times the angle, the derivative of the angle of the meg frequency squared, which our frequency is phi dot here. It's the rate of rotation. It's obviously just constant. It's just turning around and around. Let's translate this into Hamiltonian. For that, we need to first of all find the momentum, which is, let's say, we'll call it P phi because it's conjugate to the angle phi. This is dl d phi dot, and that becomes equal to I times phi dot, which you easily see by differentiating. I times phi dot, however, is the same thing as the angular momentum of the rotor. Well, now I have a problem because the angular momentum L is not to be confused with Lagrangian L. So let me call the angular momentum LZ just to distinguish it, but also if we think about the z-axis coming out of the board, it really is the z component of angular momentum of the thing rotating. All right. And then the Hamiltonian is equal to, so P phi is the same thing. The momentum, as we say, conjugate to phi is the same thing as the z component of angular momentum. Then the classical Hamiltonian is P phi times phi dot minus the Lagrangian. And if you work this out, you want to express it in terms of LZ, not in terms of phi dots. You get LZ squared divided by twice the moment of inertia. So I'll just write this again and put a box around it because this is the classical Hamiltonian. Now, what about the quantum mechanics of the rigid rotor? Here we're going to use a process of quantization. This is really ad hoc and kind of hand-wavy. It's just following intuition. But it works like this. The process of quantization is that of going from a classical Hamiltonian to a quantum one. The quantization that we've used so far in these recent lectures has been called is what is called Dirac quantization. I didn't use that terminology, but it's what it amounts to. In Dirac quantization, what you do is you take the x's and p's, which are the classical variables, and you've got a classical Hamiltonian h of x and p, and you reinterpret x as an operator, which is multiplication by x on a wave function psi of x, and you reinterpret p as a minus I h bar d dx as an operator acting on psi of x. So the wave function lives on the configuration space x, and this is transcriptions of classical variables into quantum operators, and then the Hamiltonian becomes an operator. This is called Dirac quantization, or the Dirac rules for quantization. What it takes you is not so much it doesn't take you to the Ket space, it takes you to the space of wave functions on configuration space. Now, without questioning whether it's valid or not, let's just do Dirac quantization in these other coordinates now. The angular coordinates phi and the conjugate momentum p phi. So let's apply this for the case of the rigid rotor. In the case of the rigid rotor, this suggests that phi, the classical phi, goes over into a multiplication by phi. It suggests that the wave function is going to be some wave function defined on the configuration space, which is the phi angle space. And it suggests that p phi, which is the same thing as LZ, should go over into minus I h bar d d phi. And thus the quantum Hamiltonian is obtained by replacing LZ by minus I h bar d d phi. And hence the Schrodinger equation should be this: minus h bar squared divided by twice the moment of inertia, d squared psi d phi squared, is equal to E psi of phi. This is the Schrodinger equation based on Dirac quantization. And this is easy to solve, and you find that the psi of phi is equal to e to the I m phi, where m is an integer, and if you normalize it, you have to divide by the square root of 2 pi. And m is equal to any integer, positive or negative, so it's 0 plus or minus 1 plus or minus 2, and so on like that. All right. Configuration space here is, if we want to plot this here for phi, here's the wave function psi. The configuration space only goes out to 2 pi like this. And the wave functions are e to the I m phi because they have to be, the wave function, whatever it is, it has to be periodic because 2 pi is the same as phi physically. The rotor returns to its original configuration. So the wave functions have to be periodic, and this is the solution you get by solving Schrödinger equation. That's why you have e to the I m phi's, periodic functions. That's why you get m in integers, because m has to be an integer to make this periodic. So this is a different set of boundary conditions than we had with the particle in the box. Instead of hard walls, these are periodic boundary conditions. But notice that now there's no turning points. The angle just increases in phi and keeps on going around, increasing. So the Bohr-Sommerfeld condition is going to change again, because now we won't have any 1/2 at all. It'll just be integer multiple of 2 pi. Well, to go through the details of that, let's go back to the classical mechanics, which we have to do to apply Bohr-Sommerfeld, and let's talk about the phase space for the system. So the phase space is going to be phi coordinate here and a p phi, which is the same thing as an LZ coordinate here. And we go out to 2 pi, it's the periodic and the angle phi like this, the period 2 pi. And what is the classical motion? Classical motion is obviously one where just phi dot is constant. It just rotates at a constant velocity. Or equivalently, LZ is constant. So that means a classical orbit is one that just goes straight across like this at some given value LZ, which is the constant LZ for the motion. Unlike the particle in the box, it doesn't reflect and come back. It just keeps on going. This line is the same as this line. If you like, the phase space is really a cylinder, and it just goes around and around and around. All right. So the Bohr-Sommerfeld condition has to be this. It has to be the area, which is going to be the root integral of p phi d phi, must be equal to an integer, which I'll call m instead of n now, times 2 pi h bar. With no 1/2. Let me write it this way. It's m plus 0 to emphasize that. With no 1/2 because there's no turning points. On the other hand, this integral is just equal to 2 pi times LZ. And so look what you get. You get LZ, the 2 pi's cancel, is equal to mh bar, which is the correct quantization of the z component of angular momentum. And for the energy, you get LZ, use the classical formula, LZ squared over 2I. This becomes m squared h bar squared divided by twice the moment of inertia. And these are the energy levels for the rigid rotor, the correct answer. The quantized orbits are orbits that go across here for m equals 0, so it's right on the phi line, and they're just orbits that run like this. And the area between them is a single Planck cell. Okay, so that's the rigid rotor. There's an example in the book which I think I'm going to skip. I'll let you read it in the book. This is the bouncing ball that Sakurai talks about. So this is the idea of you drop the ball and it just bounces up and down. So it's a particle in a gravitational field, except it looks like this. If I plot the potential energy, let's say of x, the potential energy V of x is equal to mgx if we're in a gravitational field. So this is the potential energy. And so the curve of potential energy is a straight line like this. Except if it's a bouncing ball, then we put a hard wall with the floor at x equals 0. And then for some energy d like this, the particle bounces back and forth between this turning point and that one. Here you've got one hard turning point with a phase shift of pi, and a soft one with a phase shift of pi over 2. So now you get an n plus 3/4 actually the quantization condition. Anyway, I'll let you think about this one. You can read about it in the book. Right. Yes.
Is the thing that makes the Poisson condition in all of these examples actually the right answer, that the potentials are going less than
Yeah, the reason these answers are all coming out exact so far is because the potential is at most a quadratic polynomial. Actually, in this case, it doesn't come out exactly. You get approximations to the roots of the area function, which you can see this table in the book gives you compares exactly the approximate answers. Before leaving this subject, I want to mention something about a multidimensional case, which is also interesting. The Planck cell in one dimension, as I mentioned, is 2 pi h bar. That's the area of a single cell. If you're in multiple dimensions, it has to be a power of this. So, for example, in 3D, you can take a three-dimensional problem. But this is the volume of a Planck cell in phase space. Planck cells are in phase space. So this is actually in the six-dimensional phase space, the position and momentum of a particle in 3 dimensions. But the basic rule is that each quantum state occupies a single Planck cell. I'll show you something you can do with this now. Let's suppose we have a region of 3-dimensional space. Let's call the region R. And let's say that its volume is capital D. And let's say that inside this region, what we've got is a free particle, but now in 3 dimensions. So its Hamiltonian is p squared over 2m, but I want to emphasize that the momentum is now a free vector, like this. So this is a particle in a box, except we'll let the box have an arbitrary shape, and it's in 3D. All right, then. Now let's let n of E be the number of eigenstates. Let's make it E naught. N of E naught be the number of energy eigenstates with energy which is less than or equal to E naught. We can call this the number function, the number of eigenstates with an energy less than or equal to a given energy. I'm going to apply this basic Planck cell rule to this, and what we'll obtain is an estimate of n of E naught as a semi-classical estimate. So, according to this idea that a single Planck cell corresponds to a single quantum state, what we need to do is to integrate the phase space volume, which is now 6-dimensional, it's d cubed x d cubed p, over all 3 position, 3 momentum variables of the region where the Hamiltonian, the value of the Hamiltonian is less than or equal to E naught, the value of E naught over here. And then we needed to divide this by the Planck cell in 3 dimensions, which is 2 pi h bar cubed. This is a 6-dimensional integral now. Looks like it's hard to do, but actually it's not difficult at all, because as far as the x, this breaks up into an x integral, which is just taken over the region R, because that's the only place the particle can be. And then it's times the momentum integral, 3-dimensional momentum integral, which is taken over the region where, let's say, the magnitude of P is less than or equal to P naught, where P naught is the magnitude of momentum corresponding to E naught, so that E naught is equal to P naught squared over 2m. Okay? Or, in other words, P naught is equal to the square root of 2m E naught. So this is easy because the first integral just gives you the volume of the region. In the second integral, you just use the formula for the volume of the sphere. It's 4/3 pi times P naught cubed. And if we put this together, we get the estimate for the number of energy eigenstates, and it's equal to the volume V divided by 2 pi h bar cubed times 4/3 pi. And then for P naught cubed, I'll write this as 2m E naught to the 3/2 power. And this gives you the answer. I could clean this up by collecting powers of pi and stuff like that, but this is the basic answer, and it shows you the structure of the formula. I'm sure you've all seen this formula before. You use this in statistical mechanics when you want to count states. Usually they make it a box, and then they use plane waves, and they count the number of plane wave solutions of a given energy to some energy less than a given energy, and you'll end up when you're all done with this formula. All I'm doing here really is to show you that what underlies those counting of states is the basic fact is that in phase space, every state occupies a cell of 2 pi h bar. And this is not restricted to free particles, although free particle makes it easy to do the integral. You can just do it applied for any system, and you get good estimates for this number function. If you differentiate this to get dn dE, this is what you call the density of states. The differentiation is easy. This is the number of states per unit energy interval, which appears in solid-state physics and all over the place. All right. So those are all examples of aspects of Bohr Sommerfeld. Okay, so this is all I want to say about WKB theory and semi-classical methods for now. Are there any questions about this before I go on? Yes.
How do turning points work in multiple dimensions?
Well, that's more complicated, and when I write a formula down like this, we're kind of blowing off the 1/2. We're just thinking that n is large enough so 1/2 won't matter. I think that's the simplest answer. The multidimensional problems are more complicated. The classical mechanics is more complicated. Some of them are integrable, and some of them are not. They're chaotic, and that affects the whole picture. In the days of the old quantum theory, people didn't understand that distinction, although they knew about integrable systems, because those are the ones that are solvable. It turns out that integrable systems have multiple periods, and that the one-dimensional Bohr-Sommerfeld rule that I've written down already gets applied to each of the periodic motions in the integrable system. And so in the period from about 1911, when Bohr worked out his results for the hydrogen atom, Bohr really did a one-dimensional problem, even though the hydrogen atom is 3D. Sommerfeld generalized this to integrable systems in more than one dimension, which is what his name gets attached to it as well. So then you get these quantization conditions, one for each of the degrees of freedom. That's the quantization rule in more detail, where you take into account turning points and stuff in many dimensions. This is a simpler approach in which I'm actually ignoring phase shifts. But it's an interesting result because it shows you that the number of states and the density of states is proportional to the volume independent of the shape of the container, which is something that would be quite hard to get by working with a wave. It's okay for a box because you know the wave functions for a box. But if you make it a blocky-shaped thing, nobody knows what the wave functions are. So this is still correct. It's only an asymptotic result, but it's still correct. All right. Okay. In the days of the old quantum theory, they didn't understand these phase shifts of the turning points because they didn't know about wave functions. So they got some answers wrong by this 1/2. The fact that the harmonic oscillators is n plus 1/2 instead of just n was something that took a while to emerge. But anyway, the answers they got were in many cases very good, and so everybody knew they were on the right track, but they didn't really understand what this quantization condition meant. Okay. All right, so I'd like to turn now to a new topic, which is the elementary harmonic oscillator, which you all have seen before. So I expect a good deal of this will be review. And there's no eraser in here. Did I cover one up? No, there's no eraser. There's no eraser in here. Yeah, well, I can't go on without eraser. So the basics of the one-dimensional harmonic oscillator, as I say, I'm sure are familiar to you, but I'm going to go through Dirac's algebraic derivation of the eigenstates and eigenfunctions and eigenvalues of the harmonic oscillator, which I'm sure you've seen before also. But it's an interesting argument, and I would encourage you to pay attention to the details of it to see how the logic flows. Dirac's algebraic treatment of the harmonic oscillator is the simplest and neatest, most famous example of the solution of a quantum mechanical problem by algebraic means. What that means is that we work with the properties of the operators and their commutation relations, but without attempting to solve the Schrodinger equation. And we don't do it by solving differential equations and worrying about wave functions. In the case of the harmonic oscillator and also in angular momentum theory, this is really by far the most effective and efficient way of dealing with problems involving harmonic oscillators. Now, what you know of your one-dimensional harmonic oscillator is a Hamiltonian, which is p squared over 2m plus m omega squared over 2x squared. This is expressing the potential energy. Potential energy is a parabolic or quadratic function here, v of x, is a function of x. This is expressing the potential energy in terms of frequency instead of the spring constant. As I expect you know, this is frequently just a small amplitude approximation to a true potential. Real potentials are never really x squared because they don't go to infinity. They have to fall. They have to flatten out somewhere. So typically, the potential energy is only this quadratic form of the potential energy is only an approximation to a real potential near the bottom of the well. Another thing to mention is that if you have a multidimensional problem, for example, if you have two dimensions, x and y, and the potential energy as a function of x and y has a minimum somewhere like this. You can imagine there's the bowl sitting down like that. You can expand the true potential without the minimum and carry it out to second order. You're going to get a quadratic form in the coordinates x and y. This is a symmetric quadratic form, and it can be diagonalized by an orthogonal transformation. And the result is that the Hamiltonian, now the multidimensional Hamiltonian, will break up into a sum of one-dimensional harmonic oscillators, generally with different frequencies. The frequencies of the so-called normal modes are usually not the same. They may be the same, but they're not always. But the point is that the quadratic approximation to a potential in multi-dimensions can be reduced to the problem of a one-dimensional harmonic oscillator looking like this. So in solving the 1D problem, we're actually solving multi-dimensional harmonic oscillators as well. I only drew this with two coordinates, x and y, but in some cases the number of coordinates is much larger than that. The famous example is the vibrations, lattice vibrations in a solid, in which case the number of coordinates is equal to the number of atoms times 3. So it could be an enormously large number. And in that case, the diagonalization of the quadratic form for the potential energy amounts to obtaining the normal modes of vibration of the solid. Actually, this could be considered a classical problem, finding those normal modes. But once you find them, then each one of them becomes a single one-dimensional harmonic oscillator, which is quantized by the methods I will present in a moment. So, although we'll be dealing with just one-dimensional problem, it's actually applicable to multi-dimensional problems also. By the way, this is a mechanical oscillator, but the harmonic oscillator Hamiltonian occurs in a number of contexts where it's not a potential energy problem. For example, a particle moving in a uniform magnetic field has a Hamiltonian which can be transformed into the form of a harmonic oscillator. Another very important example is what happens in field theory, in quantum field theory, in which the modes of a free field, whether they be electromagnetic field or a field describing massive particles, can be, again, decomposed into normal modes, and each one of those becomes a harmonic oscillator. In cases like that, the excitations of a given mode are identified with particles, and we speak, for example, of photons in the quantization of the electromagnetic field, which from a mathematical standpoint are very similar to the quantization of sound waves, the phonons, in the solid, which otherwise are just the normal modes of vibration in the solid. In any case, harmonic oscillators, this is just a way of saying that harmonic oscillators have many, many applications in physics. All right, so let's go back to the one-dimensional harmonic oscillator and do it. There are three constants that appear here, the mass, h bar, and the frequency omega. And it's convenient to avoid clutters of constants to choose units such that all three of these constants are equal to 1. An equivalent way of speaking of this is to say that if you take the given values of m, h bar, and omega, you can construct a fundamental unit of length And this is equal to the square root of h bar divided by m omega. And similarly, you get a fundamental unit of momentum, which is the square root of mh bar times omega. You get this fundamental unit of energy, which is h bar omega of time, which is 1 over omega, and so on, etc. And by choosing units like this, it's equivalent to choosing units of each of these. This length, momentum, energy, time, and so on are all equal to 1 in the unit system we choose. This is going to make the harmonic oscillator now become simply 1/2 p squared plus x squared. It's in dimensionless form now. To convert back to real units, you'd need to multiply or divide by these scale factors to get the actual units you want. By the way, I can only do this for a one-dimensional oscillator. If I had two harmonic oscillators whose frequencies were different, I can't set both frequencies equal to 1. Then I'd have to, I can still set m and h bar equal to 1, but not the frequencies. Anyway, for one oscillator, we can do this. All right, so this is a quantum oscillator, let's say, at this point. So the commutation relations of the position and momentum are that their commutator is I/h bar, except for setting h bar equal to 1, so it's just I. In Dirac's method, he begins by defining a set of new operators. One is A, which is defined as x plus it divided by the square root of 2. And its Hermitian conjugate A dagger, which is x minus it over the square root of 2. These are, the first one is called the annihilation operator, or it's also called the lowering operator. And the second one is called a creation operator, or a raising operator. The terminology annihilation and creation is typically applied to photons, the quantization of electromagnetic field, but the terminology is equivalent. Now, these two operators are not Hermitian, so they remember that, so they don't we don't diagonalize them. On the other hand, they have some nice properties. In particular, let's define a new operator, which is the product of A dagger times A. Well, just from the line above, this is 1/2 of x minus it times x plus it. If those were C numbers instead of operators, you just multiply them together and you get 1/2 of x squared plus p squared, which is obviously the Hamiltonian. But because these are operators, there's also a commutator that occurs. You see you get x times ip minus p times ix divided by 2. So you get I over 2 times the commutator of x with p. So this first term is the Hamiltonian. And the second term is I over 2 times I, because that's what the commutator is, so it's 1/2. And so we can summarize this if I bring the 1/2 over to the other side by saying that h is equal to n plus 1/2. The n operator, by the way, is called the number operator, given name. And the result of this is that the Hamiltonian is the number operator plus 1/2. The number operator has some properties here. Is that, first of all, the number operator is Hermitian, which is obvious if I take its Hermitian conjugate, it just goes into itself. And it's also non-negative definite. So n is 1 Hermitian and 2 non-negative definite. The fact that it's non-negative definite means that the eigenvalues of the number operator are non-negative. They can be positive or 0. It's easy to show that it's non-negative definite because if I take an arbitrary state phi and sandwich it around n, recall that the definition of a non-negative definite operator is that this expectation value has to be non-negative for all choices of phi. Well, let's see what this is. This is phi, A dagger A, phi, like this. This, however, is the square of the state A phi. And the square of a state is greater than or equal to 0 because that's one of the postulates of the vectors in Hilbert space. It's the definition of the Hilbert space, as a matter of fact, part of the definition. All right. So it's non-negative definite. So the Hamiltonian is equal to this number operator plus 1/2. That's just a trivial change, a constant shift. And the result is that the states of the Hamiltonian and the eigenstates of the number operator are identical, and only the eigenvalues are different. The eigenvalues of H are just the eigenvalues of n plus a half. So we're going to diagonalize n, find the spectrum and eigenstates of n first, and then H follows from that trivially. Okay, so we'll do this in the following way. The first thing I want to note is, in regard to finding the eigenstates and eigenvalues of the number operator n, the first thing to mention is that this is a one-dimensional problem. Potential goes to infinity, like this, on both sides. This means that the eigenfunctions have to die off exponentially at both positive and negative x. And as a result, it means that the eigenfunctions are non-degenerate. They're also discrete. Remember, the discrete spectrum, and they're non-degenerate, as we showed earlier in that lecture I gave on some properties of one-dimensional systems. Let's denote an eigenstate of the number operator with the symbol nu, where nu is the eigenvalue, so that n acts on nu and brings out eigenvalue nu. Now I'm using the symbol nu here because at this point, for all we know, the eigenvalue could be any number, positive, negative, fraction, integer, or anything else at this point. However, it's easy to see that nu has to be, actually cannot be negative. That's because n is a non-negative definite operator, as you see from just the line above. So whatever the eigenvalues are, they cannot be negative numbers. All right. Now, next let's consider the state nu. And we'll assume this is normalized too. Let's say that nu scalar product is equal to 1. We'll assume these eigenstates are normalized. Now let's consider the state we get when we apply the operator A, the annihilation or lowering operator, to an eigenstate of the number operator. And let's take that and let's let the number operator act on it. This is the same thing as A dagger A times nu. Now, allow me to move the A dagger past the A, for which I need commutation relations between A and A dagger, which I meant to mention before, I didn't, but I'll go over here and do it. From the commutation relations between X and P, it's straightforward to work out those between A and A dagger. So the calculation, and you find that the commutator A with A dagger is equal to 1. And so, this A dagger A, this becomes the same thing as A dagger times A acting on nu, with a minus sign of just A acting on nu. However, the A dagger A is n. The n acts on nu and brings out nu itself. And so the right-hand side is nu minus 1, multiplying A acting on state nu, like this. So, to summarize this, we have number operator n acting on A nu is equal to nu minus 1 acting on A nu. And thus we can say that the state A nu, remember nu here is assumed to be an eigenstate of n, the number operator with eigenvalue nu. And so this statement says that if we apply the number operator to A nu, we get a factor of n minus 1. Therefore, A nu is an eigenvector of n with eigenvalue nu minus 1. Except for one slight wrinkle, we have to worry about the possibility that A nu could be equal to 0. Because if it is equal to, nu is not 0, nu is normalized, but A nu could be 0. And if A nu is 0, then this equation just says 0 equals 0, and it doesn't give us anything new. So to make a precise statement, we can say that if A nu does not vanish, then it is an eigenstate of the number operator with an eigenvalue nu minus 1. All right. Now this raises the question, which is, does A nu equal to 0? When does this happen? When if at all does this happen? To answer this, we'll use the basic fact of Hilbert spaces that a vector can vanish if and only if its square vanishes. So let me remove the question mark and say that this condition is true if and only if you take the square of it, I get nu A dagger A nu, like this, equals 0. This, however, is the same thing as nu sandwiched around the number operator, which is the same thing as nu times the norm of the eigenstate, which we're assuming is normalized, so it's just nu itself. And so what we see is the answer to Wynn is that A acting on nu is equal to 0 if and only if nu is equal to 0. I'm going to put a little box around that because that's the main conclusion of this. So to go back to the formula at the top of the board, we'll say it again in light of the new information. We'll say that if nu is not equal to 0, then A nu is an eigenstate of n with eigenvalue nu minus 1. If nu is equal to 0, this equation just says 0 equals 0 and doesn't say anything. All right. Now, we can do something similar with the raising operator. Let's consider n acting on A dagger nu. This is the same thing as A dagger A, which is n times A dagger acting on nu. And now allow me to move this A to the right of that A dagger. So here's the commutator of A dagger, which is up there. And so this gives us A dagger times A dagger times A acting on nu, plus A dagger acting on nu. Again, these factors are n acting on nu brings out nu, and the result is that it's nu from this term and 1 from this term, nu plus 1 times A dagger acting on nu. So now we have the statement that nu is an eigenstate of the number operator with eigenvalue nu. When we apply A dagger to it, we get a new state, which, if it does not vanish, is an eigenstate of n with eigenvalue nu plus 1. Let's go through the same thing. Does this state vanish? When is the possibility of A dagger nu vanishing? A dagger nu equals 0 if and only if its square is equal to 0, which is nu times A dagger nu. However, by the commutation relations, A dagger nu is equal to A dagger A plus 1, which is equal to n plus 1. So we can say that A dagger nu vanishes if and only if nu plus 1 equals 0. But remember, nu is greater than or equal to 0, so nu plus 1 is always greater than 0. And the result is that A dagger nu never vanishes. So we're going to write this. A dagger nu is not equal to 0 always. So let me box this part of this. Well, so what we've got is that let's do it this way. Let's write it this way and say that n acting on A dagger nu is equal to nu plus 1 A dagger nu. And to put it in words, A dagger nu is always, if nu is an eigenstate of n with eigenvalue nu, then A dagger nu is an eigenstate with eigenvalue nu plus 1 always with no restrictions. All right. Now from this it follows that the quantity nu, the eigenvalue, has to be an integer. Because suppose nu is not an integer, then by applying an a's and a squared and a cubed and so on to the nu, like this, we get eigenvalues which are nu minus 1, nu minus 2. And we can bring this down up to the point, by applying enough A operators, we can get up to the point where nu minus k is less than 0. Well, the eigenstates of n don't have any negative eigenvalues. So this seems to be a contradiction. And the only way to escape the contradiction is to assume that nu is an integer. Because what happens when you apply these A operators is you're eventually going to get down to the state 0 when you apply n of them. And then when you apply the next one, A to it, instead of getting some state minus 1, what you get is just 0 altogether. That's when this condition here, AX on the 0 state gives us 0. So therefore, the only consistent solution to these sets of relations is that nu is actually an integer, so I'll just replace it by n, which is an integer. And in fact, it takes on the value of 0, 1, 2, and so on. it has to take on all these values, all these non-negative integers, because if any one of them occurs, you can get all the others by applying raising and lowering operators. So if there's any eigenstate at all, which there has to be, then these are the allowed values of the integers. And so thus we have the spectrum of the number operator n, that is the integers 0, 1, 2, 3, and so on. And from that it follows immediately that the energy eigenvalues are equal to n plus a half, because the Hamiltonian is equal to the number operator plus a half. All right. Now, now I want to worry about, so now the states, so now we'll call the eigenstates n. We've got nx on n is equal to n. This is the basic relation we're going to work with here. We also have A acting on n is proportional to n minus 1. And we have A dagger acting on n is proportional to n plus 1. Summarizes some of the things we've learned so far. Let me call, in the first equation involving A, let me call the proportionality constant Cn. Let's say an acting on n is some proportionality constant Cn times n minus 1. Cn is in general a complex number. To find it, we can square both sides of this equation. We square the left-hand side, we get n sandwiched around A dagger A. Squaring the right-hand side, we get the absolute value of Cn squared times the norm of n minus 1. But we're assuming these states are normalized, so that norm is equal to 1. On the left-hand side, we have the number operator in the middle here. And the result is that Cn squared is equal to n, just upon the number n. And therefore, Cn is equal to a phase factor e to the I, let's call it alpha n, times the square root of n. Like this. And so, we can now write out some of these relations, these annihilation relations here. If we apply A to the state 1, we get e to the I alpha 1 times the square root of 1 times 0. If we apply A to the state 2, the annihilation operator, we get e to the I alpha 2 times the square root of 2 acting on 0. A acting on 3, we get e to the I alpha 3. I'm just writing down some of these so you can see the pattern. This is actually not good. It's 1 square root of 3 times the state 2, and so on. This is the information we have so far from these creation and annihilation relations. Now at this point, let's take these states 1, 2, 3, and so on, and redefine them so as to absorb these phases alpha 1, alpha 2, and alpha 3. And if we do that, then we've established phase conventions for the states 1, 2, 3, and so on, and these phases e to the I alpha go away. In the process of doing that, we don't change the phase of the state 0. And what we are, in effect, doing is linking the phase conventions for all of the excited states to the phase convention for the ground state. And so, with that convention, I can erase these phase factors, and now there is only one phase convention for the eigenstates, and that's the phase convention for the ground state 0. And if we do this, then I'll draw the result in the little box here. It is that the result that I think you know is that A acts on n because this is square root of n times n minus 1. By a completely similar argument, working with the raising operators, we find that A dagger acting on n is the square root of n plus 1 times n plus 1. These are relations I'm sure you memorized for an undergraduate exam sometime, so there they are. As it turns out, it's not necessary to introduce any additional phase conventions for the A dagger equation. The phase changes that I made over here are all you need to do. Then this A dagger equation automatically follows. The effect of these phase conventions is to make the matrix elements of the raising and lowering operators in the energy eigenbasis to make those matrix elements real. And that's the most convenient choice for dealing with a harmonic oscillator. Okay, that's all. And you multiply this out, and you can see the masses will cancel. And what you get is a 2 pi times the energy E divided by the frequency. Now, by Bohr-Sommerfeld, that has to be equal to n plus a half times 2 pi h bar on the quantized orbits. And you can see we can cancel the 2 pi's here, and then solve for the energy, and the result is that the energy is equal to n plus a half times h bar omega, which you recognize as the exact answer. So without much trouble, for the harmonic oscillator, we get the exact answer for Sommerfeld quantization. Gives the exact energy levels. WKB theory does not give the exact wave functions for the harmonic oscillator, but it does give the exact energy levels. All right. Now, I'm going to run through a series of examples just because it's so easy to do them, and we might as well have some fun just getting some answers. We'll start with some answers we know on harmonic oscillator. Let me next do a particle in a box. So here's x. Here's, let's say, x equals L is the size of the box, and the potential energy is that it's 0 inside the box, but it's infinity outside. So these are hard walls. And the size of the box is L. Now, of course, the classical particle just bounces back and forth in the box, like this. To get the orbits in phase space, we need to think about phase space. So let's plot x and p. Here's the line x equals L, again. And the particle is free inside the box. Let's say it has a momentum p0, just to distinguish the momentum of the particle from the variable momentum p here. So the orbit going across on the right side it's a straight line with a constant velocity at momentum p0. And when it gets to the opposite wall, it bounces back, which just means it changes the sign of momentum. So it changes to minus p naught and goes back this way with a momentum minus p naught. And thus the orbit in phase space is really kind of a rectangle. Well, there's a discontinuous jump from here to there because it's a hard wall, but I'll fill it in like this as if it went continuously from one to the other and then back up. And you can see that the orbit is a rectangle in phase space. Now here's the tricky part about the particle in the box. And that is that instead of having a phase shift of pi over 2 at a turning point, we have a phase shift of pi. And the reason is that of an ellipse in phase space. So it looks something like this. And to use the Bohr-Sommerfeld rule, we're going to need the area of the orbit. Well, the area of an ellipse is pi times the semi-major axis times the semi-minor axis. So let's call this x max here as the maximum position for x. That's the x-intercept of the orbit. We get that by setting momentum p equals to 0, so the kinetic energy term goes away, and then solving for x. And if you do this, you find that you get twice the energy E divided by m omega squared. Likewise, let's call this p max here, which is the maximum value of momentum. That's the momentum intercept. We get that by setting x equal to 0 and then solving for p. So that becomes equal to the square root of 2me, like this. And thus the area is, you can calculate the area without doing any integrals. You know the formula for the area of the ellipse. It's pi times the semi-major axis, which is the square root of 2me, times the semi-minor axis, which is the square root of 2e divided by m omega squared. Or maybe I've got the semi-major and minor axis reversed, but it won't matter because it's just the product of the two. Now, the Bohr-Sommerfeld rules for the quantization, semi-classical quantization of one-dimensional systems. The rule itself is very simple, although we went through some pain to get it, involving area functions and asymptotic forms and so on. But the basic rule is really simple, and it has a simple interpretation also. It says that the area of the orbit in phase space, which is otherwise loop integral pdx, is an integer plus a half times 2 pi h bar. 2 pi h bar is the same thing as Planck's original constant h. So you can think of the area of Planck cell, so-called Planck cell, as being an area h in phase space. I'll remind you that the origin of this, well, let's see, just to sketch the orbits in phase space for a typical oscillator, there'll be things that look like this. And the quantized orbits are the ones that have an area of n plus a half Planck cells. So the middle one, the center one, has an area of a half. And then after that, it goes 3 halves, 5 halves, and so on. So the area of each little annular region that connects one quantized orbit to the next has an area of one Planck cell. Now, I'll remind you that the origin of this formula is the basic idea that as a particle moves around its orbit, it accumulates a phase, which is the integral of p dx divided by h bar. This is a very old idea and actually precedes even modern quantum. This goes back to the days of the old quantum theory. In any case, you can imagine it tracing out a wave as it goes around its orbit. Now, in addition to that, it loses a phase of minus pi over 2 every time it passes through a turning point. And since we have 2 turning points in a typical oscillator, that's a total lost phase. And the answer then has to be an integer multiple of 2 pi in order to get phase coherence. I'm just repeating some things I said in the previous lecture. So this has to be equal to 2n pi. And this condition in this form is the same as the condition up above. It's just rewritten in slightly different language. Here, this has to be a loop interval if you're going to go all the way around the orbit. All right. Now, that's the basics of the rule. So I'd like to begin today by making a simple illustration of how we can apply this rule. Let's work with the ordinary harmonic oscillator, where the Hamiltonian is p squared over 2m plus m omega squared over 2x squared, as I guess you know. We'll first think about this classically. If we set h equals e, we get an orbit of energy e. And if we plot this in phase space, x and p, the equation